Let's take a look at the physics of perspective. There are many people making videos explaining perspective, yet they misunderstand what it is and how it works. So let's take a moment to put perspective into perspective. Perspective is a technique originally developed by artists to make drawings look more realistic by emulating natural optical effects in order to give the illusion of depth of field in a two-dimensional rendering. This is not to say that artists invented perspective, nor did they discover it, but rather they were the original developers of the techniques we call perspective in flat renderings. Perspective is an optical illusion that can be observed naturally anywhere that we have a clear view over a distance. It's the result of mapping a three-dimensional image into a two-dimensional space, such as the retina of the eye. Our brain anticipates that an image focused on our retina originated as a three-dimensional image and processes this two-dimensional image into a three-dimensional model by reversing the effects of perspective, giving us the ability to interpret depth of field. Most folks have heard that perspective is the effect that makes parallel lines appear to converge in the distance. But in fact, while this is an effect of perspective, there is more to this illusion than that. These folks are usually aware that objects appear smaller at greater distance, but they often misunderstand just why this occurs. So, what exactly is really happening that causes the illusion we refer to as perspective? Perspective is all about the physics of light propagation and geometry. When light reflects from an object, rays are sent outward from each point in virtually every possible direction. From every point on an object, there will generally be rays of light leaving the object at an angle relative to a converging or focusing lens that will allow the light to strike the lens. The set of these rays from every point on the object constitutes one of the infinite complete images of the object radiating outward. These rays of light are refracted by the converging lens to a predictable focus point where the image is reconstituted. In a camera, this would be the imager or the film. In the eye, this would be the retina, and for a projector, this would be the viewing screen. While all the light from the object that strikes the focusing lens is available to recreate the image, the amount of light rays available to reach the lens becomes increasingly fewer with distance to the object. This effectively makes the object look smaller the further away it is, and this allows the light from more distant objects to reach the lens. The smaller the object looks, the less detail we can make out. Eventually, the light coming from the original object just sort of blends in with the more distant objects, which are at least as difficult to resolve as the original object is. At this point, where we can no longer differentiate one object from another, is called the vanishing point. Every object in the field of vision is reduced in angular size proportional to its distance from the observer, including the space between objects. This is why the parallel edges of a road appear to converge. Large objects shrink with distance at exactly the same rate as small objects do, and it does not matter even a little bit whether these objects are in the center of our line of sight or not. As the distance between the object and the converging lens grows shorter, the process is reversed. An object once lost beyond the vanishing point becomes increasingly easier to resolve. The object never actually vanished after all. Rather, the light from the object was overwhelmed by the light from behind it. That's all. No magic, no mystery, just simple physics. Now the opposite effect happens as we move away from an object. As the distance between the observer and the observed increases, the amount of reflected light that reaches the objective lens from any given object decreases, causing the image to diminish in size. As the size decreases, our ability to resolve details dissolves. It takes very little distance to make the words at the bottom of the cross illegible. After just a bit more distance, the base of the cross becomes increasingly difficult to differentiate from the surrounding terrain. Yet, the bottom of the cross is just as visible as the top, sides, and middle. The entire cross gets smaller as a unit. The bottom does not disappear first, as some have proposed. Rather, the cross just gently blends in with the background. Incidentally, the cross, as it becomes unresolvable in the distance, does not at any time merge with the horizon. From this camera angle, the horizon is well below eye level. The only way to get this object to align with the horizon would be to elevate our observation point and adjust our gaze downward. This is because perspective has nothing at all to do with the perception of the horizon. The only thing both phenomena have in common is a dependence on distance. I hope you enjoyed this video. I welcome any questions or comments you might have. If you did enjoy this video, please like and subscribe. I hope to make more science videos in the future as time permits, so click the icon for bell notifications so you won't miss the next one when it comes out. Thank you very much for watching today, and we'll talk to you soon.